Northern France, June 1944, 3 days before D-Day. A French resistance cell received coded instructions from London. Destroy the railway bridge at Saumur, a critical junction carrying German reinforcements toward Normandy. The timing was absolute. The bridge must fall exactly 36 hours before the invasion began. No earlier, no later. Too early, and Germans would have time to repair. Too late, and reinforcements would already be moving. The resistance fighters had explosives, courage, and detailed plans. What they needed was precision timing measured in hours across days, something impossible with conventional fuses that measured seconds or minutes. Then, hidden in their latest supply drop, they found small pencil-shaped devices with color-coded bands. British time pencils. Team leader Pierre Dubois examined the instructions. Each pencil contained a thin wire holding back a spring-loaded striker. When activated, acid slowly corroded the wire. When the wire weakened enough, it snapped, releasing the striker to hit a percussion cap that fired the detonator. The yellow band meant 36 hours, exactly what they needed. At midnight on June 3rd, Dubois and his team placed demolition charges under the bridge's main support columns, inserted time pencils into the detonators, and pulled the safety strips. The acid began eating through the retaining wires. The resistance fighters withdrew, establishing alibis miles away. For 36 hours, the time pencils counted down chemically, silently, invisibly. At noon on June 5th, exactly as planned, the bridge exploded. The central span collapsed into the river. German engineers arrived to find impassable destruction requiring weeks to repair. When Allied forces landed at dawn on June 6th, German reinforcements that should have been rushing to the beaches were stranded on the wrong side of a demolished bridge, delayed by an explosion that had been set in motion 3 days earlier. This is the story of the time pencil and how British chemists turned corrosion into the perfect sabotage clock. Let's go back to 1940. Special Operations Executive Saboteurs faced a fundamental challenge: how to delay detonation long enough to escape, but precisely enough to strike at the most effective moment. Conventional safety fuses burned for seconds to minutes, adequate for battlefield demolitions where engineers withdrew immediately before detonation, but useless for sabotage operations requiring hour or day-long delays.
Clockwork timers existed, but had severe limitations. They were mechanical devices the size of alarm clocks, bulky and heavy for operatives traveling light. The ticking was audible, potentially alerting guards during placement. They were fragile, easily damaged by rough handling during parachute drops or covert transport. Most critically, they had to be wound and set precisely. If you wanted a 24-hour delay, you had to calculate exactly when to set the timer, accounting for placement time and withdrawal. Station 9, tasked with developing sabotage equipment, needed something revolutionary: a delay mechanism that was small enough to conceal easily, silent in operation, reliable across temperature extremes and rough handling, capable of delays from hours to days, simple enough for minimally trained resistance fighters to use, and requiring no power source or mechanical winding. The solution came from chemistry rather than mechanics. Captain Stuart McCrae and his team developed what became officially known as the L delay, but universally called the time pencil due to its shape. Instead of mechanical clockwork counting down time, the time pencil used chemical corrosion, acid slowly eating through a thin wire at a predictable rate, creating delays measured in hours without any moving parts, noise, or power requirements. The time pencil was elegantly simple, which made it reliable and manufacturable in large quantities. The complete device measured approximately 13 centimeters long and 8 millimeters in diameter, truly pencil-sized, small enough to hide in a pocket or conceal in a cigarette pack. The exterior casing was seamless brass tubing, crimped closed at both ends. Brass was chosen for corrosion resistance and non-magnetic properties. The device wouldn't be detected by metal detectors focused on finding ferrous materials. The casing was painted with a colored band indicating delay time: black for 10 minutes, red for 30 minutes, green for 1 hour, yellow for 3 hours, blue for 6 hours, white for 12 hours, and silver for 24 hours. Inside the casing, from top to bottom, was the complete timing and firing mechanism. At the top sat a safety strip, a thin metal or fabric strip that passed through the casing and held the firing mechanism safe until deliberately removed. This safety prevented accidental activation during storage, transport, or handling. Below the safety mechanism was a spring-loaded striker pin under tension, held back by a thin wire stretched across its path. This wire was the heart of the timing system, typically lead or a lead alloy, chosen because these metals corroded predictably under acid attack. The wire thickness varied based on desired delay: thinner wires for shorter delays, thicker wires for longer delays. The acid container was a sealed glass ampule positioned adjacent to the restraining wire. The ampule contained cupric chloride solution or similar corrosive liquid, held safely away from the wire until activation. A small breaker pin was positioned to crush the ampule when the safety strip was pulled. At the bottom of the device sat the percussion cap, a small explosive primer that would detonate when struck by the firing pin. The cap was connected to the detonator socket at the device's base, allowing it to be screwed directly into explosive charges or connected via detonator cable. The activation sequence was simple but irreversible. When the operator pulled the safety strip, internal pressure crushed the glass ampule, releasing acid that flowed over and around the restraining wire. The chemical reaction began immediately, acid attacking the metal, gradually weakening it through corrosion. The wire slowly thinned as metal dissolved into the acid solution. When the wire corroded to critical weakness, a point determined by original thickness and acid concentration, the spring tension snapped it. The striker pin, suddenly released, shot downward and struck the percussion cap. The cap detonated, sending its explosive impulse through the detonator socket into whatever explosive charge was attached. The timing precision came from carefully controlled variables: wire metallurgy and diameter, acid concentration and temperature, and the chemical reaction rate between the specific acid and metal combination. Station 9 chemists spent months testing different combinations to create reliable delays spanning the range from minutes to days. Temperature affected timing significantly. Cold weather slowed chemical reactions, extending delays. Hot weather accelerated corrosion, shortening delays. The color coding system accounted for this. Trained operatives learned to compensate, using a 25-minute pencil in winter to achieve 30 minutes, or a 35-minute pencil in summer for the same target delay. The waterproofing was critical for reliability. The brass casing was sealed with soldered crimps and coated with waterproofing compound to prevent moisture infiltration. Water entering the casing could affect acid concentration, corrode components prematurely, or cause complete failure. Each time pencil underwent waterproof testing during quality control. Manufacturing was surprisingly complex despite the simple appearance. Each unit required precision machining of the brass casing, careful calibration of wire thickness, precise acid measurement, glass ampule fabrication, and assembly by skilled technicians who understood that lives depended on reliability. Production facilities across Britain manufactured millions of time pencils during the war. Time pencils saw extensive use throughout World War II across all theaters, employed by SOE agents, resistance networks, commando units, and partisan forces. The operations ranged from strategic railway demolitions to tactical ammunition dump destructions, united by the need for delayed, precisely timed detonations. Railway sabotage utilized time pencils more than any other application. Resistance fighters would identify critical rail junctions, place explosive charges against rails or bridge supports, insert time pencils set for delays that would allow the saboteurs to establish alibis far from the site and walk away. Hours later, when trains approached or reinforcements were scheduled to pass, the explosives detonated, severing supply lines at moments of maximum disruption. The D-Day preparations saw coordinated time pencil operations across France. Hundreds of resistance cells received identical instructions: activate time pencils at specific moments calculated so that explosions would occur simultaneously across northern France in the hours before the invasion. The synchronization wasn't mechanical, it was chemical, with acid corroding wires in hidden locations throughout occupied territory. Fuel depot attacks employed time pencils for delayed ignition. Saboteurs would infiltrate storage facilities during shift changes or quiet periods, place incendiary charges with time pencil igniters deep within fuel tank clusters, and withdraw. Hours later, when guards had completed their security sweeps and relaxed, explosions triggered massive fires that consumed thousands of liters of aviation fuel or diesel. Ammunition dumps were high-value targets where time pencils provided critical safety margins. Placing explosives among stored ammunition was inherently dangerous. Any accident would kill the saboteurs instantly. Time pencils allowed operatives to place charges carefully, verify connections, and withdraw to safety before detonation initiated the ammunition chain reactions that often leveled entire storage complexes. Factory sabotage used time pencils to destroy machinery during off-shifts when fewer workers were present. Resistance members with factory access would place charges on critical equipment: generator turbines, machine tools, production line components, timed to detonate overnight or on weekends, maximizing damage while minimizing worker casualties. Assassination attempts occasionally employed time pencils, though this was controversial. Several operations targeted high-ranking Nazi officials by placing time-delayed explosives in vehicles or buildings the targets frequented. Success rates were low because target schedules changed unpredictably, but the psychological impact of officials knowing they might be targeted by invisible time bombs affected German morale.
Booby trap applications use time pencils to delay detonation after demolitions, catching pursuit forces or bomb disposal teams. Engineers destroying bridges would leave secondary charges with long delay time pencils hidden near the primary destruction site. When German engineers arrived to assess damage or begin repairs, delayed explosions would catch them concentrated in the demolition area. The tactical flexibility came from the range of available delays. Operatives could select timing appropriate to specific missions. Short delays for operations where rapid destruction was needed after brief withdrawal, medium delays for establishing solid alibis, or long delays for coordinating with other operations or striking when targets would be most vulnerable. Time pencils were remarkably effective given their simplicity, but they had limitations that shaped operational planning and occasionally led to failures. Understanding these constraints provides realistic assessment of the technology. The timing variability was both feature and limitation. Station 9 specified that a 30-minute time pencil would actually detonate anywhere between 25 and 35 minutes. This uncertainty was intentional. Exact timing was impossible to guarantee with chemical corrosion, but it meant operations requiring precise detonation at specific moments faced uncertainty.
Most operations accepted the variability, but some missions requiring split-second timing couldn't rely on time pencils. Temperature sensitivity was significant and couldn't be eliminated. The chemical reaction rates fundamentally depended on temperature. Cold slowed everything. Heat accelerated everything. Trained operatives learned compensation techniques, but novice users or resistance fighters without formal training sometimes miscalculated, leading to premature or excessively delayed detonations that compromised operations. The reliability, while generally high, wasn't perfect. Approximately 2 to 3% of time pencils were duds. Manufacturing defects, contaminated acid, improperly calibrated wires, or damaged components caused complete failures where the device never fired. Saboteurs learned to use multiple time pencils on critical targets, accepting redundancy cost to ensure at least one functioned. Physical handling could damage the delicate internal mechanisms. Rough drops, crushing pressure, or extreme shock could break the glass ampule prematurely, bend the striker pin, or crack the casing and allow moisture infiltration. Operatives received training in gentle handling, but field conditions weren't always gentle. Discovery risk existed throughout the delay period. Unlike instantaneous demolitions where the charge either works or is discovered before placement, time pencil charges sat armed for hours or days. Alert guards patrolling installations sometimes found charges before they detonated, disarming them and alerting security. This risk increased with longer delays. 24-hour pencils were exposed to discovery for a full day. German countermeasures evolved as they recognized the time pencil threat. Security forces training included identifying time pencil characteristics, the distinctive brass tube, color coding bands, and standard size. Bomb disposal personnel developed procedures for safely handling discovered time pencils, though the lack of external indication of remaining delay made this terrifyingly dangerous work. Gestapo interrogators specifically questioned captured saboteurs about time pencil operation, seeking intelligence on how to identify armed charges. Some captured operatives under torture revealed time pencil details, allowing Germans to train guards on what to look for during security sweeps. German security implemented systematic searches of high-value facilities at intervals shorter than the longest time pencil delays.
If guards searched every 12 hours, a 24-hour time pencil might be discovered during the interim sweep. This forced saboteurs to use shorter delays that allowed less time for escape and alibi establishment. The Germans never developed reliable detection technology for time pencils. Metal detectors couldn't distinguish between time pencils and thousands of innocuous metal objects in industrial facilities. X-ray equipment existed, but was rare, and couldn't clearly image the device's internal mechanism. German security had to rely on visual searches and guard vigilance, methods that time pencils' small size and innocuous appearance often defeated. Beyond their direct tactical effects, time pencils created profound psychological impact on German forces and strategic value that exceeded their physical destruction. Understanding this dimension reveals their full significance. German personnel in occupied territories developed paranoia about time-delayed sabotage. Every unexplained noise, every minor incident became a potential time bomb waiting to explode. Guards walking past industrial equipment wondered if time pencils were hidden in machinery, counting down silently. This constant low-level anxiety degraded morale and operational efficiency. The unpredictability was psychologically corrosive. German forces could prepare for immediate attacks. They understood how to respond to explosions, firefights, or over-sabotage. But time-delayed explosions could occur hours or days after saboteurs had left the area, when guards had searched and declared facilities secure, when normal operations had resumed. The randomness created helplessness that conventional threats didn't produce. Resource diversion was substantial. German security forces dedicated enormous manpower to searching for time pencil charges, inspecting facilities, checking equipment, investigating suspicious objects. These searches consumed thousands of man-hours that could have been used for combat operations. Every hour a German soldier spent searching for time bombs was an hour not spent fighting Allied forces. Industrial disruption extended beyond physical damage. Factories and occupied territories sometimes stopped production entirely when time pencil sabotage was suspected, conducting comprehensive facility sweeps. These work stoppages reduced output more than the actual sabotage damage did, multiplying the economic impact of resistance operations.
Collaboration discouraged was an unexpected benefit. Civilians in occupied territories who might have cooperated with Germans became reluctant when time pencil attacks demonstrated that resistance could strike precisely and escape cleanly. The perception that resistors operated with impunity, placing bombs that exploded long after they'd vanished, made collaboration seem dangerous and futile. German morale suffered from the realization that occupation wasn't permanent or secure. Time pencil attacks demonstrated that resistance networks operated successfully despite German security. Each delayed explosion was evidence that saboteurs had penetrated supposedly secure facilities, placed explosives undetected, and escaped. This damaged the German narrative of invincibility and control. The strategic coordination enabled by time pencils had enormous value during D-Day. The ability to coordinate hundreds of simultaneous sabotage operations across France, all timed to strike within the same narrow window before the invasion, created disruption that conventional attacks couldn't achieve. German response to the invasion was delayed and confused, partly because their logistics had been systematically destroyed in coordinated time pencil operations. Time pencil technology continued after 1945, evolving through the Cold War and influencing modern time delay demolition systems. The fundamental principle, using chemical reactions for timing, proved so effective that variations persist in contemporary arsenals. Military forces worldwide adopted time pencil concepts for special operations. U.S. forces developed similar chemical delay fuses during and after the war, incorporating lessons from British designs. Soviet forces created their own versions based on captured samples and intelligence reports. The simplicity and reliability made chemical time delays attractive for irregular warfare scenarios where mechanical timers were impractical. Commercial demolition industries adopted time pencil principles for controlled explosions in mining, quarrying, and construction. Modern commercial time fuses use similar acid wire corrosion mechanisms, though with improved safety features and more precise calibration than wartime military versions. Terrorist and insurgent forces in various conflicts have used time pencil type devices or similar chemical delay mechanisms.
The technology isn't classified. The basic principles are published in numerous sources, and the materials are readily available. Counterterrorism forces train specifically on identifying and disarming chemical delay devices that descend conceptually from World War II time pencils. Electronic time fuses replaced chemical delays in most modern military applications. Digital timers offer precise control, adjustable delays, remote activation and deactivation capabilities that chemical systems cannot match. However, chemical delays retain niche advantages. They require no batteries, generate no electronic signature for detection systems, and are immune to electromagnetic interference. Museums display time pencils as artifacts of sabotage warfare. The Imperial War Museum, the Churchill War Rooms, and various resistance museums across Europe preserve examples. Cutaway models show internal mechanisms, and displays explain the chemical principles. Some exhibits include recovered time pencils that failed to detonate during actual operations, silent witnesses to sabotage attempts decades past. The color coding system became standard for other time delay devices. Modern commercial and military time fuses often use similar color bands to indicate delay durations, a convention that traces directly to Station 9's time pencil design. Academic studies of irregular warfare consistently cite time pencils as exemplifying effective low-technology solutions to complex problems. Military historians analyzing sabotage effectiveness highlight time pencils as force multipliers that gave resistance networks capabilities disproportionate to their size and resources. The time pencil looked like nothing, a brass tube small enough to hide in your hand, containing acid, wire, and a spring.
No electronics, no complex mechanics, nothing that suggested it could coordinate sabotage across entire countries or destroy facilities hours after the saboteurs had established alibis miles away. Yet this simple device gave resistance fighters what conventional weapons couldn't, the power to strike precisely timed blows against occupation forces. British chemists understood something profound. Time itself could be weaponized, not through complex clockwork or electronic circuits, but through chemistry, acid corroding metal at predictable rates. That understanding transformed sabotage from random destruction into precisely coordinated operations that struck when they'd cause maximum disruption.
For resistance fighters operating under German occupation, the time pencil represented hope and capability. It meant they could attack high-value targets and escape before Germans even knew sabotage had occurred. It meant they could coordinate their strikes with Allied operations, becoming part of a larger strategy rather than isolated nuisances. It meant they weren't helpless against occupation. They had tools that worked. The Germans searched endlessly for time pencil charges. They implemented security protocols, trained guards, conducted sweeps, and captured saboteurs who sometimes revealed details under interrogation. Yet they never effectively countered the time pencil threat because they couldn't search everywhere continuously, couldn't be certain any location was secure, couldn't eliminate the fear that somewhere acid was corroding wire and bringing them 1 second closer to explosion. So why was this clever British time fuse perfect for sabotage strikes? Because Station 9 chemists created reliable timing through corrosion rather than mechanics. Because the device was small enough to hide, simple enough for minimally trained resistance fighters to use, and precise enough to coordinate operations across hundreds of miles. Because time pencils turned every saboteur into a precision instrument, every resistance cell into a force capable of striking exactly when it would hurt most. The mathematics of sabotage changed with the time pencil. Before it, saboteurs either detonated charges immediately and fled, or used unreliable delays that might or might not work. After it, they could walk away from targets with confidence that destruction would occur hours later, timed to Allied operations, synchronized with other resistance strikes, calibrated for maximum disruption. That's the difference between random violence and strategic warfare. The time pencil made every resistance operation a calculated strike in a larger campaign. And in occupied Europe, where every bridge destroyed, every rail line severed, every fuel depot burned helped Allied victory, the timing mattered as much as the destruction, sometimes more. The brass pencil that turned time into a weapon didn't win the war alone, but it helped. One corroded wire at a time, one precisely timed explosion at a time, one German supply train derailed exactly when it needed to be stopped at a time. And sometimes, in war, helping is enough. From time pencils to shape charges to rebreathers, World War II weapons reveals how British innovation turned simple chemistry into strategic advantage. Subscribe now for more incredible stories of weapons that changed warfare through brilliant engineering and precise timing.